Welcome back to Meaning from Data, Statistics Made Clear. In fact, this lecture makes that title particularly pertinent because in this lecture we're going to be discussing experimental design. In previous lectures we've talked about statistical inference and discussed things such as taking random samples from a population. And we discussed the idea of hypothesis testing, which involved making a hypothesis about the null hypothesis with some hypothesized view of the world and then gathering experimental data to decide how rare the experimental data would be under the hypothesis of the world, and then rejecting that null hypothesis if we found that it would be a rare thing to find the data we found given the null hypothesis. And then in the last lecture, we discussed the notion of confidence intervals, which were a measure of how sure we were that the sample that we got from the population really was representative of the whole population. But often, the way that we get these data are to do experiments. We undertake experiments for the express purpose of obtaining data that is amenable to analysis. So that's the challenge of experimental design, to make sure that we gather the data in such a way that we are able to draw the meaning from the data, that we are able to use the techniques of hypothesis testing and confidence intervals to make the mathematical kind of deductions that make logical sense and that allow us to actually infer from the data the ideas of interest. There was a very famous statistician who lived at the beginning of the 20th century by the name of Ronald Aylmer Fisher. And he was a pioneer in many parts of statistics, but in particular in experimental design. One of the famous cases involving Fisher occurred at a tea party, where he was at this tea party and there was a lady at the tea party, and they had tea which included drinking milk in the tea. So it was common to have milk in tea, and this was common in those days. And this lady at this tea party asserted that she could tell just by tasting whether the milk was poured into the hot tea or whether the tea was poured into the milk, and then in both cases stirred. Well, of course, what are you going to do under these circumstances if somebody makes such an outrageous claim? You have to design an experiment in order to gather evidence that will help us decide whether or not the lady's assertion was correct. And Ronald Fisher was at this party, and this is, I believe, an actually accurate thing, something that actually happened. That he was at this party, and on the spot, he devised an experiment which was intended to detect whether or not the lady could in fact detect the difference of whether milk was poured into the tea or tea was poured into the milk. And here is the experiment that he devised. What he did is he took 20 cups of tea, 10 pairs of cups of tea. And for each pair, in one of the cups, he put the tea, then the milk, and in the other cup, he put the milk, then the tea. And then presented the lady with a pair of cups. So he gave her a pair of cups, and he said, one of these cups is milk, then tea, the other is tea, then milk. And the lady tasted the cups and then said, this one is the milk first cup, this one is the tea first cup. And then the next pair of cups were brought out, and the lady did the same testing, and then the next pair of cups were brought out. And of course they were randomly put which side was the milk first one and which side was the tea milk one. That was just randomly done, so it wasn't as though every single time the left-hand one was the milk one first. And then 10 pairs of these cups were given to the lady, and then she had to, she made her decisions each time. Well, this is in a way, an excellent example of the design of an experiment where the results of the experiment can be usefully used to make the determination that we're intending to try to make. So the reason it is a useful experiment is that we have a concept of the likely outcomes of this experiment if, in fact, the lady were not able to detect the difference between milk first or tea first. You see, if she were not able to detect the difference, then it would be a 50-50 proposition for each pair of cups, whether she was right or wrong. So we can look at this chart, which gives us an analysis of our expectations of how many times she should have been right or wrong if she were in fact just guessing. Now you'll recognize this as a classic example of hypothesis testing. The hypothesis would be that she was not able to detect the difference, that she could not detect the difference at all. By doing the experiment, or before doing the experiment then, we'd have a concept of the distribution of likely results if a person who couldn't tell the difference made guesses. If you made 10 guesses and you really only had a 50% chance of guessing correctly, it would be rather rare to get 9 or 10 of them correct, or even 8, 9, or 10 of them correct. More often, you would get between 3 and 7 correct by just luck. Well, so the design of experiments idea here is that you've set up the experiment so that when you get a result, you can interpret it. Now, Fisher himself talks about this experiment in one of his books, but in his book he doesn't actually say whether the lady could tell the difference or not. But it was reported by somebody else who was at the party that in fact the lady actually was able to tell on all 10 occasions that which one came first, the milk or the tea. So if that in fact is a result of the experiment, you can see that from this graph we can see that it is a very unlikely proposition for her to have gotten all 10 correct by randomness alone. It could have happened, but it would be a very rare occurrence for that to happen. And so the experiment, by being designed in this way, we could say it's so rare an occurrence for that to have happened by accident that we will say that we reject the null hypothesis that she can't tell, and we accept the alternative hypothesis, which is that, in fact, she can tell the difference between milk first or tea first. Well, this is an example of experimental design, and notice, by the way, we would have to decide how to interpret a result of 8 correct or 9 correct or 7 correct. That we see what's going on in reality, and then it's up to us to decide how much evidence we're going to believe to be persuasive about her ability to detect the difference. Well, the context of an experiment and our beliefs about the underlying possible causes or lack of causes can influence how we interpret the results of an experiment. For example, suppose we couldn't think of any possible physical or chemical reason that there'd be a difference between the milk first and the tea first. Suppose we thought we couldn't think of any reason. Then we might be very skeptical of this, and we might think, well, maybe the lady somehow was able to see into the kitchen where the tea cups were prepared, or maybe somebody came in and told her what was going on. But if you think about it, maybe there are some physical reasons. I mean, maybe if you have a cold milk there and a hot thing hits it, maybe that it scalds it in a certain way that doesn't happen if the milk goes into the tea. It's possible to think of some potentially detectable physical difference. And so if we can think of that, then we accept the results of this experiment more readily. So that is a question. One of the purposes of the design of experiments is to try to decide, to try to avoid serious mistakes that you don't want to make. And this we have to realize that statistics is all about coming to conclusions that are not certain. They're just conclusions that are likely to be true. And for example, in our last lecture, we talked about confidence intervals, and we saw that we did an analysis that gave us a 95% chance of capturing, in that case, the actual proportion of voters who are going to vote for a given candidate in our interval. But we were sometimes wrong. So one of the issues that we have to deal with is the fact of potential error in statistics, and then design our experiments so that the errors that are bad are avoided. Well, there are actually two kinds of errors that are very common and famous for in hypothesis testing, which is the core idea, such as the example we just had. The two kinds of errors are imaginatively referred to as type 1 errors and type 2 errors. Let's remember what kind of things can happen during a hypothesis test. Remember, the idea of the hypothesis test, like the lady tasting tea, is we make the null hypothesis that, in this case, that she couldn't tell the difference, and then we declare that if the result would happen only, and then we choose a number such as 5% of the time, that if the result would happen only 5% of the time under the null hypothesis assumption, then we will reject the null hypothesis. We'll reject the null hypothesis, and that's the conclusion of our statistical inference. Well, occasionally what can happen is that just by accident alone, the experimental data will be in that 5%. It will lie outside this region. In other words, if our null hypothesis, we view it as a distribution of what would happen with a sample, such as the lady just randomly choosing yes or no for each cup of tea, it would randomly happen that she would occasionally get it right many times, like 9 or 10 times. But it would only happen, say, less than 5% of the time. So if she got it correct just by accident alone, and we rejected the null hypothesis that she were just guessing, then we would have committed a type 1 error. Type 1 error is that we reject the null hypothesis even though the null hypothesis is true. A type 2 error, on the other hand, is the opposite. It happens if the reality of the world is actually different from the null hypothesis, but we fail to reject the null hypothesis. You see, and this happens in this region. Suppose that we get data, so here the null hypothesis is this dotted line. So these are the results that would come about if, in the case of the lady tasting tea, the null hypothesis that she was just guessing. Well, suppose that she actually could get it right, say 80% of the time. So the null hypothesis was false. In fact, she was good at it 80% of the time, but sometimes she would miss. And suppose during the experiments, she happened to miss more times than usual. So the experimental result came in this region. Well, this is the region where we do not reject the null hypothesis. So we would be committing a type 2 error. A type 2 error is an error where we fail to reject the null hypothesis even though the null hypothesis is wrong. Let's think about the jury system. Remember, when a defendant is on trial, the judge in such a situation is saying to the jury, this is an innocent defendant. You must undertake your deliberations with that in mind. This is an innocent person. Now you look at the evidence. And if the evidence is unlikely to have occurred under the assumption that the juror is innocent, then you find the defendant guilty. Framed in terms of type 1 and type 2 errors, the American jury system is strongly saying, try to avoid committing a type 1 error. You see, a type 1 error would be where the null hypothesis is in fact true, that is, the person is innocent, and yet the jury condemns the person, finds them guilty, then that would be committing a type 1 error. So the admonition to the jury that judges should make, and in fact I think we should advocate this and have this become part of American jurisprudence, is that the judge should say, your null hypothesis is that the defendant is innocent, and you want to avoid a type 1 error by making the p-value of your statistical significance less than 0.01. You see, and then that would be useful, and then all jurors, I'm sure, would instantly know exactly what to do. So a type 1 error would be to convict when the juror is innocent. The other side of the coin, a type 2 error, occurs if the defendant is actually guilty. You see, so the reality here, this is the graph here. The reality is that the defendant is guilty, but the evidence was not found to be sufficient to reject the null hypothesis that the defendant was innocent. So those are type 1 and type 2 errors. Well, Fisher said, now returning to Ronald Fisher, Fisher really began his career at an agricultural research station in England. And when he arrived, he discovered that there was lots of information, there were lots of data that had been gathered over many years about crop yields, rainfall, fertilizer usage, but that the way the data had been collected made it very difficult for him or anyone else to draw useful conclusions from the data. Because many of the variables involved were confounded with each other. That means that several different aspects of the growing conditions were changing at the same time, so you couldn't tell what feature of the difference was causing the resulting change. So, for example, you have things like the kind of fertilizer you were using, the kind of soil, the amount of water. These are all variables associated with how tall the crops are likely to grow. So if you want to confidently assign an effect to a particular kind of fertilizer, for example, what you need to be able to do is to disentangle the possible effects from the other variables. Well, if you focus on one variable, one basic experimental design that will help you to get an answer about one variable is to fix all the other variables. In other words, make everything else identical and just have the one varying feature change. For example, here are two contrasting experiments involving two kinds of fertilizer, and we'll see which one will give evidence that would likely to be interpretable. In one experiment, suppose you take a particular kind of plant, of corn type A, and you put it on a hill, and where a field that's on a hill, and you use fertilizer type 1. And then you take corn type B, and you put it in the valley, and you use fertilizer type 2. Well, suppose one of the crops grows better than the other one. What can we conclude? Well, not much, because we don't know whether the difference in the fertilizer was the reason for the difference in growth. It might have been the valley versus the hill. It might have been the type A versus type B corn. So we don't know what the result really is telling us. There might have been significant reasons for the difference, but we don't know what caused them. So a better experiment would be to have all of the variables the same except for the fertilizer. So that is to say, if you could plant the things, the same kind of corn, you put it in exactly the same kind of soil, you had the same amount of irrigation, the same amount of sunlight, but you used a different fertilizer in different parts of it. And it would be better if you put the fertilizer really very close to itself, like in alternate rows. And better yet, instead of alternate rows, it would be better if you randomly put the fertilizer in different rows, in case there was something like the soil happened to lie in streaks where some of it was richer in alternate rows, you see. By doing it random, by making randomness a central part of the way you design the experiment, you could get better results, more likely to get better results. So if you fix all the factors except for the one of interest, that's an excellent way to do an experiment. So let's look at an example, though, where you have more than one variable that you're interested in. So here's an example. You have fertilizer 1, fertilizer 2, corn type 1, corn type 2. And you want to ascertain the effect of the fertilizer and the corn type. A good way to accomplish a design of experiments so that you can get meaningful data would be to try to have all combinations present in your experiment. In other words, you don't just use fertilizer 1 with corn type 1, but instead you use fertilizer 1 with both the corn types and you use fertilizer 2 with both the corn types. The effect of this, you can see this table here, and these are potential data. Suppose that the average height, the mean height of the plants that had fertilizer 1 and corn type 1 were 80 inches tall. Now, by the way, I don't know what is the height of an elephant's eye, but I think this should be as high as an elephant's eye, and it may be 80 inches. And then here with fertilizer 1, corn type 2, 60 inches tall. You see, and maybe the mean is 70 inches tall. Well, if we have this data from all of our experiments, it's helpful in making a conclusion. For example, we can just look at this one row and see that fertilizer 1, for the different corn types, this is telling a difference in the way the corn types are affecting the growth. And if we look down the column, we see that 80 here and a 40 here would mean that fertilizer 2 applied to the same corn type gave a much smaller growth. So this is suggestive of the idea that fertilizer 1 was efficacious in its application to corn type 1. Now, by the way, it's not 100% clear how we can interpret these data even as they are, because there's no indication in this chart about the standard deviation of the data. If there was a lot of spread in how tall the plants were, we may not be able to make robust conclusions about this even from these data. So looking at all different combinations and designing your experiments so that all the variables are combined allows us to disentangle the influence of the different variables and analyze the experiments in many different ways. There are other examples of experimental design that bring up other issues. In medical experiments, real effects often come when there's no physical cause at all. And you've got to take these effects into account when you're trying to test new medications. That is, we have to consider seriously the placebo effect. It turns out that people are very susceptible to the suggestion, particularly by a trusted doctor. If a patient comes into a doctor and the doctor says, here's a pill that's a wonder drug for your ailment, you'll feel better almost instantly. Well, it often happens that indeed the patient does feel better. And even if the actual pill itself has no active ingredient that could be the cause of that. Well, so the placebo effect is a fact, but it makes testing of drugs more difficult. Because if we give some people a new drug, say for curing the cold, and they get over their colds more quickly than people who didn't take the drug, we don't know whether it really was the drug that did it or whether there was some sort of placebo effect that was accomplishing it. So we've got to figure out an experimental design that rules out this placebo effect. So a basic design to study the efficacy of drugs then is to take a population of people who have the disease that you're interested in testing its efficacy on, and give half of the patients the drug and give the other half of the patients a placebo, and not tell the patients whether they're getting the placebo or getting the drug. So the intent is that if there's an average difference in the outcome between the patients who got the placebo and the patients who got the drug, then we would be able to attribute that difference to an actual effect of the medication. But it turns out in real life that there's actually another aspect that you have to take into account in medical testing, and that is that the experimenters themselves, the people giving the drugs, are often not unbiased observers. They are hopeful that a particular medication will work. And if there is something about the experiments that involve judgment, for example, if you ask somebody, how are you feeling today? Or you're saying, how much pain are you in? Do you hurt? If you have an experimenter who has a vested interest, that person may hear the result quite differently from somebody else. So the interpretation of whether the patient has improved is sometimes a judgment call on the basis of the experimenter. This is another characteristic that needs to be taken into account when you're doing the when you're doing experiments about medical tests. So it has been found that it makes a difference whether the experimenter knows that this particular patient is getting the placebo or this particular patient is getting the drug. So there are the kind of experiments that are done are called double-blind experiments. These are experiments where neither the patient nor the people who are directly in contact with the patients or administering the drugs or assessing the progress of the medication, that none of those people knows whether the individual patient had received the real drug or just a placebo. So that is the strategy, and that is the gold standard for medical tests, double-blind experiments. Of course, it's also important that the other characteristics of good experimental design, such as choosing patients randomly, are also used. And by the way, this placebo effect works not only in medical arenas, but the Hawthorne effect is a famous effect that was named after a Western Electric plant in Cicero, Illinois, where experiments were conducted between 1927 and 1932. And the goal of the experiments originally was to determine the effects of things like lighting and humidity and these kinds of variables on the worker productivity. But what happened is that they discovered that no matter what change in the lighting and humidity were done, it had a significant positive effect on the workers' productivity. The idea was that just being looked at turned out to have a very positive effect on people's work. One of the issues that are very important to avoid in experimental design is the concept of the lurking variable. The lurking variable refers to the idea that there may be something that's causing a change in the thing that you're trying to experiment with, but that you haven't actually taken into account in your experimental design. And there's a great example of this that comes from Ronald Fisher's work in the agricultural station. One of the fields was called Broadbach Field, in which the wheat output, in the measured wheat output, had an interesting occurrence. It turned out that in 1876, the output of the wheat in that field got quite a bit worse, and then got even worse in 1880, and then improved again in 1894, and got worse in 1901 for no reasons that were associated with the experiments that were being done on the field. It turned out there was a lurking variable. In 1876, the Education Act was passed in England, which made school attendance compulsory. It turned out that before that time, little children were hired to weed the field. And so they would pull the weeds from the field, and that would help the wheat grow. So when this Education Act was passed, they were not out there available to weed the gardens and the field, and so the wheat production went down. In 1880, they actually made penalties for people who kept their kids out of school, so the production went even further down because fewer kids were there. But then in 1894, a headmaster of a local girls' school thought that good physical activity was important for girls, and so he had the girls going out pulling weeds as part of their physical activity. And this increased the wheat production in that field until 1901, when he died, and the next headmaster didn't have that same philosophy. The girls quit pulling weeds, and so the wheat production went down in the field. This is an example of a lurking variable. Other examples of lurking variables. Suppose that you want to know, are married people paid more than unmarried people in the workforce? Well, answer, yes. In fact, people who are married for 10 years are paid more than people who are not married. Why? Well, because they're older. People who are married tend to be older than people who are unmarried on average, and consequently you would expect them to be paid more because of their age. The age is the lurking variable. Designing experiments in order for us to get good results is a very tricky business, and it allows us to think ahead to the kinds of statistical strategies of inference that we're going to use. This concludes part 1 of the course, and in part 2 of the course we're going to take different application areas and see examples of statistics in action. I look forward to seeing you then.